Hi friends, may Tuesday bring you good luck. I always pray for your happiness. The questions in this series are similar to the previous video. It's just that the method is different. This time we will get the acceleration at a test point using the Eulerian description. This is intended so that we can understand the difference between Lagrangian and Eulerian descriptions when measuring data. For those of you who don't know what a nozzle is, the display on the screen is an illustration of a nozzle. The length of the nozzle is 0.4 meters. Because the inlet velocity is lower than the exit velocity, the inlet diameter is larger than the outlet diameter. Thus, this is the inlet. This is the outlet. Let's say the center of the inlet and the center of the outlet are on the x-axis. And the vertical line is the y-axis. In this series, we will use the Eulerian description. In this approach, we only observe the physical quantities at the test point. We want to calculate the acceleration of the fluid particle when the particle reaches a point 0.1 meters from the inlet. We will sample the space at point 0.1. At this point the fluid has a velocity v. In three-dimensional space, velocity is a function of four independent variables, x, y, z, and t. We can write the velocity v like this. What does it mean? That each point on the x-axis can have a different velocity. Each point on the y-axis can also have a different velocity. Each point on the z-axis also has a different velocity. Each point at the same point at different times can also have different velocities. Thus v of x, y, x, t can describe the velocity of the fluid in the nozzle at a certain time. Velocity is a vector quantity. In addition to having a magnitude, velocity also has a direction. Thus, velocity has vector components on the x-axis, y-axis, and z-axis. Let's say the velocity component on the x-axis is u. The velocity component on the y-axis is v. And the velocity component on the z-axis is w. Thus the vector v can be written as ui hat plus vj hat plus wk hat, where u, v, and w are also functions of the four independent variables. Using the Eulerian approach, the acceleration value can be written as the partial vector v partial t plus u partial vector v partial x plus v partial vector v partial y, plus w partial vector v partial z. This symbol is the operator of partial derivatives. This equation contains the vector v, so we will calculate the velocity vector first. Assume that the fluid velocity satisfies the linear equation. We can write the velocity as the vertical axis. Point 1 is a point at the inlet, its coordinates are 0, 1. Point 2 is a point at the outlet, its coordinates are 0.49. Connect these 2 points, a straight line will be formed. Well, this straight line equation is a velocity equation. We can use the concept of a straight line equation that passes through 2 different points. This equation can be written as follows: v minus 1 is equal to 20x. From here, v is equal to 20x plus 1. Since the particle is moving on the x-axis, of course this is the velocity component on the x-axis. Previously we have heard that the fluid velocity field is often written in the form of component vectors. We have known the value of u. Vector v is equal to 20x plus 1, I hat. Now, write the acceleration equation. Assume that the fluid flow through the nozzle is a steady flow. Thus the magnitude of the fluid velocity at the same point is constant. The partial factor of the vector v partial t is 0. Since the fluid only moves straight along the x-axis, there is no contribution of the velocity components on the y-axis and z-axis. The factor of the partial vector v partial y and the partial vector v partial z are also equal to 0. The velocity components u and v vector have been known. I think we have understood the concept of derivatives correctly. The partial derivative of 20x plus 1 with respect to x is 20. The acceleration vector is 400x plus 20 I hat. This acceleration vector is a function of the variable x. At the test point, the value of x is 0.1 meters. This is an easy calculation. The magnitude of the acceleration is 60 meters per second squared. This value is positive. This means that the particle will move accelerated from left to right. An important concept of the Eulerian description is that we only need to know the location of the test point. Even though we do not know the mathematical equation of a fluid flow, we can place an acceleration sensor there. The value read on the sensor is a value that matches the Eulerian description. Happy learning, everyone!
I like to be educated, but I'm so frustrated. Hello to my